Hello and welcome back to the Biochemistry for Health Sciences channel. In today's video, we'll continue the applications of enzyme kinetics, and we will discuss or try to answer this question: how good is an enzyme? In a previous video, we talked about these three values: the maximum velocity of Vmax, turnover number or Kcat, and Michaelis constant or Km. Just to remind you, so if you look at this graph here, the maximum velocity for this enzyme is 100. Remember, this graph was obtained by increasing substrate concentration and determining the velocity, and the concentration of enzyme is fixed. So the concentration of enzyme does not change, only the substrate increases. So the velocity is the maximum velocity that this fixed amount of enzyme can catalyze the reaction, and that comes out to be 100. So once we know the maximum velocity of Vmax, we can then calculate the Kcat by dividing the maximum velocity with the concentration of enzyme that was added to this series of tubes. So Kcat is basically the number of substrate molecules converted into product molecules per unit time, such as per second, by each molecule of enzyme. So that's the turnover number or Kcat. So from the Vmax, we can also find the Km, the Michaelis constant. So if the Vmax in this case, in this example, is 100, we take 50% of 100, which is 50, extrapolate it to the curve, and bring it down to the x-axis. So we extrapolate it to the curve, bring it down to the x-axis, and here we get a substrate concentration of 10 millimolar. So the Km for the hyperbolic curve, the blue curve here, is 10 millimolar. For the sigmoidal curve, instead of Km, we often use S0.5 or K0.5, and that happens to be also 10 millimolar. So that's how we got these values that we discussed in the previous videos: maximum velocity, turnover number Kcat, and Michaelis constant Km. So now we should be able to answer this question: how good is an enzyme? And the answer to the question is the catalytic efficiency. What is the catalytic efficiency of the enzyme? And that is equal to Kcat divided by Km. So once we know the Kcat value of the enzyme, we divide it by the Km, and we get what we call the catalytic efficiency. So the catalytic efficiency will tell us how good is an enzyme. Now, a perfect enzyme will have a catalytic efficiency of around 10 to the power 8 to 10 to the power 9 per mole per molar per second. Okay, 10 to the power 8, 10 to the power 9. That will be a perfect enzyme. So what do you mean by a perfect enzyme? That means every time this enzyme encounters a substrate, as the substrate diffuses to the active site, it is immediately converted into product. Okay, so if there is a perfect enzyme, this catalytic efficiency should come out to be around 10 to the power 8 to 10 to the power 9. So, is there a perfect enzyme? Do we have a perfect enzyme? So let's look at a few examples of enzymes and look at their catalytic efficiencies. So here are a few examples of enzymes. So remember, the perfect enzyme would give us a catalytic efficiency of around 10 to the power 8 to 10 to the power 9. So let's look at this enzyme first, acetylcholine esterase. The substrate is acetylcholine. This enzyme is the one that breaks down acetylcholine. Acetylcholine is a neurotransmitter, so it is released by neurons, and these neurons could be synapsing a muscle, the muscle, or another neuron. And to make sure there is no excess acetylcholine, the enzyme breaks down any excess acetylcholine. If that doesn't happen, then the muscle will remain contracted, and that can lead to very serious consequences. So acetylcholine esterase, very interesting. If you look at the Kcat divided by Km, the catalytic efficiency, that is a perfect enzyme. So we're talking about an enzyme that is perfect, 1.5 times 10 to the power 8. That means every time an acetylcholine enters the active site of this enzyme, it is broken down. Carbonic anhydrase, using the substrate of carbon dioxide. This enzyme we discussed in a previous video, very important for acid-base balance, has a very high catalytic efficiency also. So we are talking about 10 to the power of 7. So almost a perfect enzyme. Then we have catalase. We talked about this enzyme in a previous video. This enzyme breaks down excess hydrogen peroxide, because if we don't break down hydrogen peroxide, that can give us free radicals and that can damage the cells. So once again, plays a very important physiological role, so not surprising, a perfect enzyme. So these enzymes play very critical roles in physiology and biochemistry, and not surprisingly, they have very, very good catalytic efficiencies. Chymotrypsin, we did discuss this enzyme in the previous video. This is a protease that breaks down certain proteins, and so this enzyme is very important in digestion as well as in lysosomes. So using an ester as a substrate, we see that this enzyme is very far from being perfect, has a catalytic efficiency of only about 2. So perfect enzyme has to have something around 10 to the power 8. So this take-home message here is that we have enzymes, some of which are perfect on one extreme, and then there are enzymes that are very, very far from perfection. So the answer to the question, how good is an enzyme, is to calculate the catalytic efficiency, Kcat divided by Km. And if the enzyme has a value in this range, it's perfect, and enzymes that have very low values are far from perfection. So yes, we do have biomolecules in our body that are perfect. In future videos, we will continue discussing more important features on enzyme kinetics applications. So until next time, have a wonderful day, and we will hopefully see you soon.